We were here before, right?
Yeah, this
So anyways,
is
this is the
you have explained it.
I have explained it, but I'm going to elaborate on that. So I'm going to go back a little bit. So we were going to, we looked at the generalized Langevin equation by the same method, but now for non-Hermitian variables. And the dynamical variable, to remind you, is a non-Hermitian. So A of t here is a non-Hermitian variable. And when you do that, then things change quite a bit. So, and there's a lot to be learned here. So I thought that it is appropriate that I go back and kind of construct that background for you, because otherwise uh, you you kind of don't learn some of the big things that are happening here. So you have had quite a bit of exposure into the Kubo product itself. You have had a little bit of exposure from the most recent discussions on using other scalar products, and these would be the anti-commutator, commutator, and the anti-commutator scalar products. So yeah. Now, it turns out whether you use this equation 3 or equation 4, whether you use the commutator or the anti-commutator, your the differences are relatively minor uh, in terms of constructing the recurrence equations for these systems. And as you saw last time, the recurrence equations do change. And I gave you the results, but I didn't show you how. So one of the things that comes to play here is this relationship. This relationship is the central relationship that guides what happens when you have non-Hermitian systems, non-Hermitian dynamical variables. So the Liouville operator acting on x comma y is negative of the Liouville operator when it's acting on y. So the scalar product goes like that. Now, what I told you last time is that the way this is constructed, typically the recurrence relation, is you generalize the first basis vector f1, which already was ILF0, but now you generalize it and you bring in a dependence on f0, which is a different kind of dependence. This one is a time evolution type dependence. This is a time independent dependence. It's not really time evolution, it's a commutator, but it has implications on time evolution. And this guy has implications on the basis vector, earlier basis vectors properties itself. And so you introduce this alpha 0, and I claimed that this alpha 0 is this IL f0 f0 over f0 f0. But this is not new. You have seen this guy before. This is the susceptibility, typically. Remember when we studied the spin operators, this was SXJ type quantity. That was susceptibility. Now it is IL f0 f0. And the next step when you go up, again, you have ILF1 plus delta 1 F0, which is something we had before. But now, instead of alpha 0 F0, you get this alpha 1 F1. What is not entirely obvious here is that the way you construct them, I've only given you the results. The way you construct and use this orthogonal, use these basis vectors actually changes. Okay, so that's the reason why I went back here, because this was something that I did not emphasize, neither did I feel a need to emphasize. But it turns out that because the orthogonality, the way it is being applied, that will be affected by the definition of equation 5. This will have an implication on how these recurrence relations are going to be affected. Of course, we have the usual conditions that F1 should be orthogonal to F0, F2 must be orthogonal to both F1 and F0, and so on. And these are the driving conditions that help us construct the generalized formula for the recurrence relation, giving us the Fs. Now, and I also mentioned to you that delta 1 turns out to be the same as before, and hence you can imagine that delta nu would turn out to be the same as before. But alpha 1 has this peculiar form, IL F1 comma F1. So denominator is not all that different, but one vector up, one basis vector up, and the numerator is unique. It's IL F1 comma F1. Here it was F1 comma F1. The basis of constructing this relation still remains the Gram-Schmidt process, which I had mentioned earlier. So if you continue with the Gram-Schmidt process, then you find that Gram-Schmidt takes you here. This is the form of Gram-Schmidt. This is a form from Gram-Schmidt. So Fi plus 1 will depend upon F1, Fi minus 1, and then Fi minus 2 all the way down to F0. This is something that if you look at the basic Gram-Schmidt in any mathematical physics book, you will find this is what Gram-Schmidt will give you. So the question now arises that what is the structural form for this second recurrence relation? The structural form for the second recurrence relation actually does not involve all these guys. And that's what I need to explain as to why that is the case, because it's a very important thing. Now, the structural relation which you see in equation 8 only involves 4 terms. Previously, it used to involve 3 terms. Now it only involves 4 terms. And in fact, what the delta nu is and what the alpha nu is, they are kind of given away by these forms, excepting you make the appropriate changes. If it's delta nu, it's F nu over F1, F nu minus 1, F nu minus 1. And if it's alpha nu, it's I L F nu, comma F nu over F nu, comma F nu. So it's actually the details are different. And because I was doing it at the tail end of my lecture last time, I did not have a chance to elucidate these subtle points. The details are quite different. Also, the other big difference in detail is, yes, it is tied to Gram-Schmidt, but all these other, these C's or sizes, they all fall away. They don't enter. Why? Now, once you have come here to 8, the rest of the journey is identical to what we have had earlier. You plug in the F news into the Heisenberg operator equation. The Heisenberg operator equation, which is the main equation we're solving, already brings in the A news. And then you do the exact same thing as we did earlier. And you get now, instead of a 3-term, you get a 4-term recurrence relation for the A news. So the 4-term structure here precipitates a 4-term structure for the A news. And because it is a 4-term structure, the structure of the continued fraction also is slightly altered. It's more generalized. So my contention is that it is in understanding how equation 8 comes that the main work has been done. And this is always the formulation. So suppose now you have a non-Hermitian dynamical variable. Suppose you also have a non-Hermitian Hamiltonian in which you are somehow balancing out with an added term energy conservation, because non-Hermitian Hamiltonian typically means energy is not conserved. So you can put in some kind of artificial energy conservation. Suppose that's your system, which would be more complicated than this. You can now, once you understand what I'm going to do, construct the recurrence relation for that problem using the same process that I'm going to do. Okay. So that is the reason why this is the protocol that we need to use to get to the higher recurrence relation. Is it more or less clear so far? Okay. So, yeah, because you might want to write down a few things. Otherwise, it's delicate enough that it might slip off from what I'm saying. So let me now go to the actual sort of inner workings. Let's now so-called open the hood of the car and take a look inside the hood. What's going on? So here are my own calculations. I've actually not done something terribly systematic. I was just doing my own calculations to check and make sure that I understand where things come from. And so I did this in writing in pencil as I do, and then I gave it to AI, and AI converted it to this form. But this is of course given IL x comma y is x comma ILY, but now with a minus sign. This is given. This, as I said, is the primary governing condition that we need to heed by, this guy. So now let us put some faces on x and y. So IL F0 is x, F1 is y, is minus F0, which is x again, IL F1. Similarly, IL F1 comma F1 by this property is minus F1 IL F1. And IL F0 comma F0 will certainly not be 0. Unlike before, because before what happened was, the moment you did IL F0, it will just give you F1, and F1 and comma F0 would be orthogonal, so that would give you 0. So clearly, this is not orthogonal. So now, because it is not orthogonal, you postulate F1 is, of course, there is IL F0 like before, but now there is a minus alpha 0 F0. Minus sign helps out, so that's why the minus sign is there, and it's by convention. Nothing fundamental about this minus sign. So now we know that this F1 must be orthogonal to F0. That's the only property we know because it's the first basis vector. Agreed? So there's no problem here. So F1, F0, by definition of orthogonality, should be 0. There is no way to dance around that. So that we have to accept. So IL F0, F0 and minus alpha 0, F0, F0 are the survivors. And they jointly can be 0. But we cannot argue F0, F0 is 0. So they cannot individually be 0. Right? We cannot argue. If we argue this is 0, then this must be 0. Or alpha 0 must be 0. So there's no problem then. Then you are contradicting yourself by saying that I need the alpha 0, but then you are showing alpha 0 is 0. So that is an inconsistent solution. So therefore, you have to agree that if the left-hand side is 0, then alpha 0, this guy that we have added, see the minus sign helps us make it positive definite. Alpha 0 becomes IL F0 comma F0 over F0 F0. Scalar product. So this is also the reason why IL F0 comma F0 is not 0. So we now have a form for alpha 0, and this is in fact the general form. So I will just assume for our own purposes that alpha nu has the exact same form, IL F nu comma F nu over F nu. And we'll see that that will happen. I'm just giving you the answer. So now let us go to F2. Again, we have to accept F2, F0 must be 0. We also have to accept, without further ado, that F1, F0 is also going to be 0. So therefore, this term and that term are both 0. And now you get a passport to find delta 1. So delta 1 now becomes, now you see there's a plus sign. So delta 1 now becomes minus ILF1 comma F0 over F0 F0. Okay. And minus ILF1 comma F0 is F1 comma ILF0 by this formula. This guy. So clearly we can see that this becomes the structure of F1. And you see, although ILF0 is not equal to F1, this is the big point. Although ILF0 is not equal to F1, ILF0 is ILF0 has F1 and alpha 0 F0. It turns out that when you couple F1 comma F1, F0 comma F1 will still be 0. So alpha 0 doesn't enter. You only have F1 comma F1. So ILF0 on the right side of the scalar product, in spite of F1 having this structure, becomes F1, F1. Because the other term becomes 0. You see, F1 comma F1 is ILF0 comma F1, alpha 0 F0 comma F1, scalar product. F0 F1 is 0 by definition. So therefore your delta 1 definition in a backhanded way is still the same as before. Although, and this is the point I'm making, although ILF0 is not F1, but F1 comma ILF0 is same as scalar product, is same as scalar product of F1 comma F1. And it is because of this behavior that I am going through this in detail. That when you change this dynamical variable, the delta 1 or the delta nu definition actually remains the same. But that doesn't mean the F nu definition remains the same. F nu definition is generalized, but delta nu definition is the same. And now you have a different alpha nu, and that is your alpha nu. So the recurrence relation that you get for the non-Hermitian system is a little bit trickier, but you get the results just fine. Of course, it affects the calculations also. So F1 IL F0 minus alpha 0 F0, then this is what I just was telling you. If you punch it with F1, you punch this with F1, this may not be 0, but if you punch F0 with F1, it's got to be 0, by definition. And so you get the delta 1 and the alpha 1 as we talked about. Sorry, sensitive. Where did I end up? I haven't been here. Why am I going forward only? Hang on. Yeah, this is where we were. So in general, we can go back to Gram-Schmidt and tell us what the formula should be. And Gram-Schmidt comes back and tells us, look, guys, if you're just applying Gram-Schmidt blindly, this should be the structure you're going to start from. Now we have to see how much simplification is possible. Now, orthogonality conditions demand that fi plus 1 comma f1 should be 0, fi plus 1 fi minus 1 should be 0, and all the way fi plus 1 comma f0 should be 0. So what is physically the meaning of this? Mathematically, we all agree that these are orthogonal f's by definition. What is physically the meaning? It's very different actually. Go back to the system in which you have spent some time. The system in which you have spent some time, on which you are now studying the memory function, hopefully, are spin operators. Spin operators in a Hamiltonian of some sort. Simple Hamiltonian, transversizing, xy, that kind of stuff. So if you imagine calculating an fi plus 1 comma fi scalar product, you will be involving the string of operators for fi plus 1 and multiplying that with a string of operators for fi. Right? What would that give you? That would give you interacting spin operators in some sites. For example, it may give you an sxi plus 1 and an syi plus 1. And then you can take a product, it's in the same site. So ISZ xy, so ISZ I plus 1. I being the square root of minus 1. Or if it were SYSX, it's minus ISZ I plus 1. But there'll be a factor of 2 that will come. You have to be careful. In this case, it won't come because we're using spin operators. If you use Pauli matrices, there'll be a factor of 2 that will come. Anyway, but the other operators that don't interact, they remain. For example, if you have an SZI or an SXI minus 1, I minus 1 is not going to interact with I plus 1. They're in different sites. They're different operators. They're not interacting. The operators have to be in the same site to interact. So what would a product like fi plus 1 comma fi give us? It'll actually give us some complicated mixed bag correlation functions, such as, just as a, I'll make up an example. The typical correlation function may be like, you know, sxi plus 1 comma szi, not comma, sorry, sxi plus 1 szi sy I minus 1 sxi minus 2, blah, 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 blah. It's a complicated multi-spin correlation function. That's what each of these guys would give you. Ensemble average. So this will give you its own set. That will give you its own set. This will give you its own set. And some of them will be imaginary. Because this should be real, you can check it out. Most likely it will go away. At least at infinite temperature, the imaginary ones will go away. At finite temperature, they will not go away. So here comes another important point. These scalar products, they actually are still not observables. And because they are still not observables, in general, they could be real or imaginary. Okay? They have no obligation to be an observable quantity, so they don't have to be real. Even our relaxation function in general will not be real. However, when you take the Fourier transform of the relaxation function and construct what would be called a dynamic structure factor, only the real part of that would be experimentally observable. That's the only real part. The imaginary part of it, if there is any, that will not be experimentally observed. So you have to be very careful. There is no guarantee that these guys are real. In fact, at finite temperature, in general, they are not real. And you will see today that even in this problem, if you do a little bit of finite temperature calculation, it will not be real. So what I'm telling you is that the scalar product of fi plus 1 fi plus 1, fi minus 1, all of these being 0, connect correlations that come in from here, and correlations that come in from here, and correlations that come in from here, and so on and so forth. Because they have to satisfy this massive set of coupled equations. So physically, what can it mean? Physically, it means that in your Hamiltonian, this is Hamiltonian specific, in your Hamiltonian, these correlation functions are mutually tied up because each of them are 0, right? So it implies, without doing any direct calculation by you, it implies that these correlation functions are related. So for example, let me give you a simple example. Let's say SCJ, SX, J minus 1. Let's say this correlation function is equal to SYJ and SXJ minus 1 or something like that. Something along those lines. That's what it means at the simplest level. Now, these are bonus gifts. You did not do any calculation to find these relationships between these correlation functions. They are just being thrown up by the machinery of the method. By construction. Construction meaning your Hilbert space construction, your scalar product choice. So these orthogonality conditions, therefore, have this beautiful message that their internal correlations are related. Okay, and this plays a big role in simplifying your problem and giving you deep insights. So, in fact, I would argue that while we are increasingly living in a state where in subject like physics, non-trivial quantities are very, very difficult to calculate, right? We live in a world like that. So we have to resort to something like direct diagonalization of large matrices to calculate physical quantities, or we have to live in a situation where we have to do maybe many powers of the matrices have also to be diagonalized, often the case in dynamics, not just not just the matrix itself, but matrix square, matrix cube, matrix 4, matrix 5. So that's impossibly difficult. While all of those are true, if you can do very, very high quality theory, then you acquire the ability to learn more about the system without doing direct work, even for very non-trivial systems. That is the reason why this is so special. Okay. And I don't know if I told you, but when I was doing my thesis calculations, in that problem, or in all those series of problems, the Hilbert space dimension was finite. And of course, just as a matter of precaution, I was checking all these orthogonalities, just to make sure that I didn't have any extra term anywhere. I mean, I was learning this game just like you are now. And I realized that I found this whole series of identities between correlation functions of the various dimensional transversizing systems I was studying, where the field goes to zero. So that way the Hilbert space dimension becomes finite. And I just couldn't control my excitement. I was completely blown away that, my God, I could find these beautiful relations, and nobody in the literature seems to be reporting them. And this is for three-dimensionalizing model that you cannot solve directly. So, both elated and somewhat mystified, I made an appointment. I went to my advisor to ask him uh, why this was happening from here. I mean, I was not expecting them to come from this kind of a relation, this kind of a set of identities. He said, well, I also didn't think about it because I've never checked these carefully. So you are the first one I know who's checking these carefully. You better check them carefully and let me know what's going on. So I got very energized. I stayed up like several nights. You know, those days you couldn't get to journals online. So I had to go to the UGA library, which was a very, very good library actually. And I pulled out old physical review papers where, you know, some citations seemed of interest. And I found there was this 1967 paper by a fellow who did his PhD with Fisher when Fisher was quite young at King's College in London. I think his name was Burridge or something like that, last name. And I found that in that paper, Fisher and Burridge had actually calculated these separate correlation functions and they had found them to be identical. So my discovery was corroborated by this 1967 study. And so I knew that I was right. But I was astonished to see that the 1967 paper in Physical Review by Burridge was like a 70-page paper. Because Burridge actually did the calculations. And I did not know the calculations. I completely unaware of Burridge's work, I discovered the entire set of Burridge's results and more by doing this back-ended business. And that taught me how powerful these are. So I actually wrote a little paper on this, which nobody ever cites because nobody understands uh, this thing unless you cast it in the language that Fisher did in those days. And these are basically, they go under identities between correlations. And they're only known for the Ising model. And that too only known for the Ising model in 1D and 2D. So my 3D discoveries that came out of it was not in Burridge's paper, if I recall correctly. So, and I could do it in D dimensions. Forget about 3 dimension, I could do it in D dimension. So, you know, these kind of things, but the same idea can be applied even when D goes to infinity. It has nothing to do with the Hilbert space dimension. So you can actually extract correlation functions in infinite infinite Hilbert space dimensional models using these identities. So they're extremely powerful. But it was in this 1992 paper in Physica A in which I had written this. And I think some of my juniors who did work on these problems, they have cited that work because this work was pretty unique. But nobody else has ever cited it because I don't think anybody understood what I wrote, simply because it is so unusual and obtuse to what we learn. Anyway, so you can just now generalize that what alpha I would be. Alpha I will have this structure, IL Fi comma Fi over Fi comma Fi. And delta I will be Fi comma Fi over Fi minus 1 comma Fi minus 1. So you can see this involves Fi's in the numerator, this involves Fi's in the numerator, but denominators look quite different. There's one scalar product below that one. And you can now write down the C of I level, and it has this format. And this particular format works out basically to 0. That's what I just showed you. Same property as here and so on. So it works out to 0. Now, the reason why it works out to 0 is because you see this is I. This is Ij. And that is all you need for all the XCIs to be thrown out under the banner of the identities between the different operators that I just said. So that relationship, this relationship here. Sorry, again going the wrong way. This relationship here. You see, when I and J, they're all I and J format. The moment you have I and J format, these all become 0. And so all the XCIs become 0, which is the reason why you can generalize the form of F nu. I've gone through the whole calculation here, but I don't need to show you. All of these are designed to show that the XCIs go away. And that gives you okay, I did not mean to come here. I wanted to. Sorry about that. That gives you this form, equation 8. Because the XCIs are not there. You stop your series in alpha nus, and that's the end of it. And you also get those correlation functions as a bonus for your studies that the power of the method throws up. You see, there is also another little learning lesson here. Mori's 1965 papers, 2 papers, they defined this whole problem. They set it up. The credit undoubtedly goes to Mori. However, Mori didn't discover this connection. I discovered the connection. Why? Because when you take a problem, difficult problem, and when you don't completely break it down to pieces in such a way that you can put the pieces together and see the whole, you will lose some. You will lose insights. And so Mori never got this insight, although he developed the beautiful method. It was much later when one restricted to Hermitian systems and Hermitian dynamical variable, one got a series of results. And the extension was made specifically for Hermitian systems and non-Hermitian dynamical variables. That's when all these finer scale details began to emerge and they became operationally useful. I didn't discuss with you when I talked about the lattice problems that Professor Yu had done, but there was a student who had worked on lattices with all these fancy geometries like the Fibonacci lattice. Fibonacci lattices have a certain pattern of numbers in how they are laid out. For example, square lattice has 4 neighbors, and everywhere it's 4 neighbors. Fibonacci lattice maybe, starts out with a lower number of neighbors, and the number of neighbors goes up because the lattice geometry is different. So in those kind of problems, this method was applied. And so things were discovered there also, because you only learn about a method by applying the method to an actual physical problem. Theory itself builds on the actual physical problem-based insights. And that is what we are trying to do. That's why this is so important. Okay, now let me see if I can go back to where I was. So essentially, I've explained to you how this thing comes about. I won't go any deeper. And now the first recurrence relation, the broadened one, when you put that into the Heisenberg equation, like before, you now have another 4-term relationship for the A's. Again, with the same structure, A of minus 1 of T0. Now, what, however, doesn't change Well, it does change a little bit. This term, this alpha 0 A of t in the generalized Langevin equation now becomes a new term. See, this was not there before in the generalized Langevin equation that I had discussed. So once you put these in, if you go back and see the treatment I had done earlier, once you put this equation 11 and equation 8 into the solution of the Heisenberg equation of motion, you take that solution, plug it back into the Heisenberg equation of motion. Then you get, through some rearrangement, this generalized Langevin equation. Now, Heisenberg equation of motion in quantum and Newton's equations of motion in classical are basically the same thing. They're both Liouville equations. They are just one is classical, one is quantum. One is Poisson bracket, one is commutative bracket for the Liouville operator. Right? So in both cases, you will get this generalized Langevin equation. But there is an interesting thing going on. You see, we all agree that in the classical problem or in the quantum problem, the Newton equation or the Heisenberg equation, they're basically operator or dynamical variable equations. You have to go to the Schrödinger equation to go to an observable equation or some kind of an observable type equation. Here it's not. It's an operator version. It's your Heisenberg picture. So naturally, when you get the generalized Langevin equation to come out, you will also get an operator equation, and that's exactly what you get. You get A dot of t minus some scalar quantity A of t. Here is an A of t prime with a kernel, and here is an f of t. No surprise there. So where is the surprise? The surprise is in the structure of the memory function phi. That's a surprise. So what is the surprise? The surprise here is that if you recall, I told you that the memory function is actually tied to the a's, small a's, and the small a's have temperature dependence in general. Right? Because we cast the problem in a canonical equation. Small a's have temperature dependence. If small a's have temperature dependence, then the memory function should also have temperature dependence. So here you have an operator equation that seems like it might have temperature dependence entering through both phi and alpha 0. Both of them have temperature dependence. Turns out that if you actually work out this problem fully, all the temperature dependence terms should go away. So temperature dependence enters because you chose to cast this problem in a Hilbert space with a scalar product defining the Hilbert space where there was temperature dependence. Your scalar products had intrinsic temperature dependence because scalar products involves a canonical ensemble average. That's where the temperature dependence came in. So let me just quickly show you. If you go back here, this is where your temperature dependence came in, right? So your temperature dependence came in, and that temperature dependence got parameterized into the deltas and the alphas. And as a result, it got parameterized all over the inner workings. And so your memory function came out temperature dependent. However, your Heisenberg equation of motion or Liouville equation or Newton's equation, that's not temperature dependent. So ultimately, whatever you do, your temperature dependence got to go away. Otherwise, you have made a mistake. It has to be gone by the time you're completely done. So therefore, it means that in this problem, By the time we reach equation 16, all our temperature dependence is buried deep inside. And once you solve equation 16, for A of t, the big A of t, your dynamical variable has no temperature dependence at the end of the day. However, you know it has temperature dependence. So it has a message. And the message is as follows. The message is that you can solve this problem at the operator level for any temperature. It doesn't matter. As long as you do it right, all that temperature dependent mumbo jumbo will go away. Ultimately, you'll be left with the skeletal operators after you finish all your calculations. So whether you solve a dynamical problem, parameterize this way at infinite temperature, at zero temperature, at some finite phase transition temperature, it does not matter. Your A of t is your A of t. That's what it says. It's very profound. So temperature enters as a parameter of convenience. Now that convenience may be a huge convenience. Nobody is doubting that. But at the end of the day, this entire machinery takes care of itself. And like a genie, it vanishes. You're left with an operator results. So this is the most amazing part of an approach like this. And that's why this approach is so famous. It originally started being called as the projection operator approach. That was introduced by Zwanzig in the late 1950s. Mori cleaned it up with this parameterization, and then Lee cleaned it up further by simplifying it, which gave all these relationships. So, and applied it to the various models just to make sure that one could learn to use this method. And there are several other groups, notably Italians, based in Pisa. They were the ones who really made it a very powerful and multi-use method. For example, in solid state physics, when we take a material, we want to know its band structure. That way we know about its conduction properties. That way we know about its, resistivity and so on and so forth. So band structure is like a critically important need for a material. In material science, we go by band structure. The same approach was adopted to solve the time-dependent Schrödinger equation, which I won't do it with you guys. But the same approach was used to solve the time-dependent Schrödinger equation. And then, with the transformation T goes to minus I beta, finite temperature field theory uses it. With that transformation, the time-dependent Schrödinger equation was put into temperature-dependent Schrödinger equation. The same approach was used to solve it. And it gave you band structure. So this became another way of calculating band structure using the very same approach. I did not put it here, but let me type it up in this slide so you can look it up. Text box. It was introduced in this very famous paper by Haydock, Volker Heine, who was his advisor, and I forget the name of this guy. I think it's, let me look it up. This is the paper, M.J. Kelly, 1972. Let's give you the reference also. So in 1972, this was Roger Haydock's PhD thesis. Haydock was Volker Heine's student. Volker Heine was a professor in Cambridge. Um, and this is where electronic structure and local environment. They essentially they skip a lot of steps here, and they give you the band structure formula. And here, instead of your scalar product like we did, they use the Green's function as a scalar product, which is also another clever thing that people do. Okay. And once they did that, they got the whole result packaged in terms of this GIJ, and from there they could calculate the band structure. It's a long, long thing. This is your band structure.
Oh, you mean to be sharing a paper with us? Because we still see your slides.
Oh, you do? You don't see this, is it? Sorry about that.
That's okay.
Let me, let me first type it up. MJ Kelly, J Phys C. Let me see. I'll give you the full reference so it's easy to pick up. J Phys C 52845. So volume 5, starting page 2845, 1972. This is the paper. So you might want to capture that. Tell you what, I'll do even better. I'll just mail you that paper. How about that? Because it's not necessarily trivial to look at this paper on the fly. But I don't want to get into this topic because it'll be very complicated. But nor am I an expert on this. I'll send you this thing. I just sent it to you by email. You should have received it, hopefully. Did it come? See.
Yeah.
Not yet?
Yeah.
Yes.
Yeah,
You
got
got it. Tony got it?
No, not yet.
Okay, good, good. You got it, right? No, not yet. It's taking longer to travel inside Buffalo than around the world.
So electronic structure based on the local atomic environment
Yes,
for
yes.
tight binding bands.
Ah, that's the paper. Hang on, why did Tony not get it? Did it complain? Check it again.
Yeah, still nothing. My last email from you. Oh, got it. That's so
Okay.
weird.
It's funny. Just traveling a few miles, it took a long time than traveling half the world. Okay. So, yeah, that's the paper. Based on basically the same idea. Okay. And this was really developed first by Haydock, Heine, and Kelly. Haydock went on to become a professor at University of Oregon. Haydock has retired now. So Haydock became a very famous person. Heine was already famous. And Haydock pioneered the whole approach in its semi-commercial form now. And the PISA group actually connected the dots and pointed out how you can go back and forth between the Maury-Lee approach, Swansik-Maury-Lee approach, and the Swansik and Heine-Haydock version of it. One was doing dynamics and dynamic structure factors and all that, and one was doing band structure calculations. So it's sort of revolutionized how we look at many things. However, none of these methods are easy because they carry a lot of load in them. Mean field theory is much easier because it doesn't carry this load. But if you want to do detailed studies, there's nothing better. Now, before I take you back to the example of Hong's study of the non-Hermitian system, which is what I touched upon last time, right? I think I touched upon Hong study. I did not touch upon this, which is the basis of Hong study. So that's why I'm here today. Hong studied the XY spin-half XY model. Spin-half XY model is technically as difficult as the two-dimensional Ising model. Technical difficulty level, same. Two-dimensional Ising model has only Ising degree of freedom, SZ coupling, right? SZI, SZJ. One-dimensional XY model is one-dimensional, all right, but it has two spin degrees of freedom. SXI plus 1, SY plus 1. So two spin degrees of freedom and one lattice dimension is of the same order of difficulty as two lattice dimension, one spin degree of freedom. Okay, so one-dimensional problem, Heisenberg model has xi plus 1, yi plus 1, SZI plus 1. One lattice dimension, three spin dimension. This is same as three lattice dimension, one spin dimension difficulty. And that has never been solved. Ising model in 3D has never been solved. However, one-dimensional Heisenberg model also has never been solved. But who else but Hans Bethe figured out what the solution might look like without doing much calculation. He couldn't solve the problem. But he was clever enough to figure out what the solution should look like. And that, in fact, is the working hypothesis even today. This paper was written by Hans Bethe when he was in his 20s, about 21, 22 years old, in Zeitschrift für Physik in 1931. One of Bethe's early papers. And it's called Bethe Ansatz. Bethe's guess. P-E-T-H-E, Bethe Ansatz solution. It's not a solution, actually. It gives you it blabbers out the result as if it came through divine intervention. And that's how Bethe solved this problem. So anyway, I'm not going to give you Bethe's result. I'm going to give you how the XY model got solved, because this solution turns out to be a fascinatingly important solution in physics. By the way, you will hear something called the Lieb-Schultz-Matisse theorem that is different than this. Okay, so this paper was written by these three people. Elliot Lieb, who was a professor in Princeton, he still is, actually he's in his 90s now, still active. Ted Schultz, who I don't know where he went, and Dan Mattis, who is retired now at University of Utah. Dan also is in his 90s, someone I know really, really well. So this paper was written in 1961, and this was about as important as Bethe's paper. So what is the point of this paper? I'll show you a few slides that capture the main points of this paper. They wrote this Hamiltonian for the XY model in the following format. You can see this 1 plus gamma, 1 minus gamma. This is a standard trick. If you set gamma to 0, it becomes what one would call an isotropic XY model. XX and YY are equally weighted. If you set gamma equal to 1, then it becomes just XX, which is same as an Ising model. Excepting instead of ZZ, you have XX. But physics is the same. If you set gamma equal to minus 1, it becomes YY, same as Ising model. So gamma equal to 1 and gamma equal to minus 1 recovered the Ising model. Gamma equal to 0 recovers the XY model. So this model is built with two built-in limits that are known, and the middle part if they want to solve, and anywhere else. And of course, they brought up the Pauli spin operator here, because that's what they are. And it turns out how the chain ends of the chain are always very important in any problem. Boundaries are extremely important in spin systems. Okay. So I'm not going to spend time on this because we are now interested in infinite chains. So boundaries can be pushed back to infinity. But the common condition used is periodic boundary, like here, Sxn plus 1 is Sx1, Syn plus 1 is Sy. And I goes until n minus 1 because the interaction is set up as I plus 1. So the last one will be n. So anyway, I told you what the gamma's range is and this. And now the question is, how do you solve this problem? Here you see there is a Z also that is coming because he's talking about the generalized Heisenberg model, which is the beta problem I told you. But they are not going to do that here. Okay, let's take it's about a few minutes past 3. We'll take a 5-minute break. How about that? And then we'll resume. I'll just stop the recording and then remind me to start the recording. Wait a minute. What happened to this? I'll just stop the recording for pause recording. Pause. Okay. So anyway, so we finished this part. Next comes this guy. So what happened was that, and this is a very routine thing that people have to do when dealing with a second quantized way of looking at the Hamiltonian. Have you guys done second quantization?
A little bit, yeah.
Okay. Vivek, have you done second quantization?
I'm not sure.
Okay. So second quantization is basically what we are doing now. This is called second quantization. So second quantization, why it's second, you will know in a second. But the point about second quantization is that spin operators in general are relatively complicated operators. Spins are neither fermionic nor bosonic. So if you are dealing with spins, then you cannot take advantage of the known statistics of fermionic and bosonic systems. So the idea that Deep, Schultz, and Mattis introduced here is how to take a spin operator system and move it to fermionic language. That's what they did. They moved it to fermionic language. Now, since then, people have also moved it to bosonic language. The bosonic language process is called bosonization. You will find hundreds of papers in PhysRev on bosonized Hamiltonians. Second quantization is basically fermionization. Here you are fermionizing it. That's what we are doing. And there are advantages to that. So first step of that is introducing these quote unquote raising and lowering operators involving the spin operators. So Sxi plus Isyi is Ai dagger. This is your raising operator. This is your lowering operator. Yeah, very simple. So using the raising and lowering operator language, you can write Sxi as Ai dagger plus Ai because then the imaginary terms cancel out. And similarly, you can write Syi as Ai dagger minus Ai, but you have to cancel out the I, so there is an I in the denominator. And Szi can be expressed as Ai dagger times Ai minus a half. And so with 2.2b as your way to travel from the Ai language to the Sxi language and so on, by using this, you can rewrite the Hamiltonian in this form. equation 2.3. So you have an AI dagger, AI plus 1. You have this guy. You have the AI dagger, AI plus 1 dagger. If gamma is 0, isotropic case, then the second term drops off. This term is only gamma dependent, this term. So gamma equal to 0 drops off. And the Hermitian conjugate of this. Basically, you take the conjugate of this. So just for keeping life simple, imagine gamma is 0. You're doing the isotropic XY model, then the second term is not there. But there is a problem in the current transformation. The problem is that these AIs, they partly relate to the Fermi operators because their anti-commutator is 1. And if you apply them twice in a row, they become 0 because you can only raise and lower. That's all you can do. You can't raise twice, then it becomes lower. Basically, they're creation and destruction. You create and destroy. You can't keep on creating without being careful. So if you create twice on the same thing, it's already created. Why? You cannot create anymore. So that's why it becomes 0. Now, they also partly resemble Bose operators because their commutation properties also hold. They commute very nicely. They don't anti-commute. But because this is I not equal to j, the main property that matters is this property. So point is that this property is tied to Bose operators. So therefore, the AIs essentially are partly Bose operators, partly Fermi operators. But this should not be a surprise because I already told you that the spin operator is neither a boson nor a fermion. It has properties of both. So you are basically representing spin operators. So it is neither a boson nor a fermion. It has properties of both. So what happens now? So this transformation, this quote unquote first quantization is not enough. You have to go to second quantization. What is second quantization? Now you have to make another set of operators that are made out of AIs and A daggers, which are only fermionic or only bosonic. In this case, only fermionic. So the CI, this is the new operator, is defined basically as a Fourier transform of AI, similar to a Fourier transform. It's not really a Fourier transform, but it is similar to a Fourier transform. Some quantity here, which is like a presumably it becomes a scalar quantity and acting on AI. And similarly, CI dagger is the same thing with complex conjugate. These two mean the same thing. It's just complex conjugate of one and the other. However, the Hamiltonian is not much affected because CI dagger CI is same as AI dagger AI. And the inverse transformation, if you instead of going from AI to CI, if you want to go from CI to AI, you just flip the sign and flip the operator. Like an inverse Fourier transformation type idea. And here you get pure Fermi operators. CI, CJ dagger, anti-commutator is delta IJ. And otherwise, they are 0. No problem, pure bosonic operators, pure fermionic operators, I'm sorry. But now the Hamiltonian acquires this form. It is just a minor twist on what we had earlier. This half comes in. I'll take you back to the earlier one. Oh, here also there was a half. So you see, this was the structure before with AIs. Very same structure. Properties are a little bit different, but the operators. Now it's the same structure.
No, it's a completely fermionic Hamiltonian.
Now it is a completely fermionic Hamiltonian.
It kind of feels like magic. How did that just happen?
That's why I use the word, it is like a Fourier transform.
Okay.
You take a product of these two, the I pi's, this I pi, this part, they cancel each other, but the operators now are turn out to be Fermi operators. Actually, what is not addressed here is the Z part of the spins. This works well for the XY part of the spins. The moment you put the Z part of the spin as Zi plus 1, which was what Pater did, then it becomes more complicated. But for the XY part, this looks simpler. So this second quantization transformation is particularly suited for the XY Hamiltonian. Don't get the wrong impression that it is suited for all spin Hamiltonians. The symmetry is almost built magically for the XY Hamiltonian. Okay, so that is partially answering your question, Tony. Now, there is a message in this problem. And the message is, this is creation, this is annihilation, of course. But this is a way in which you are describing the interaction between the ith and the I plus 1th fermion instead of a spin operator. You have gotten rid of spin operators completely in this picture. And if you have boundaries, then you have to take into account this extra term that comes in, which is obviously more complicated looking. And that's why I said that I will not talk about boundary conditions because it complicates matters. So here, this is the piece that comes in. And therefore, if you have periodic boundary condition, this is the piece that enters your Hamiltonian also. So that's where you're paying the price. The boundaries are affected. And it is important to emphasize that in all quantum mechanical many-body systems, boundaries play an outsized role also, along with the nature of the Hamiltonian. You know, the Hall effect, for example, is all because of boundaries. So many Nobel Prizes have gone to Hall effect of a conductor. Hall effect is a boundary effect. Boundaries can be non-trivial. You have also seen, for example, when we did the XY model, semi-infinite, that edge spin you could solve exactly. That's what we did when we studied the semi-infinite XY chain, which you checked. However, the bulk spin is much more complicated and very different in physics. It shouldn't surprise you if I take a ruler, the surface of this ruler is much more prone to breaking than this part of the ruler, because this is an edge. There's no coupling above, but this guy is coupled on the right and left and up and down. So interactions change fundamentally at the edges, and that effect shows up here. This is why I thought I should introduce you to this a little bit, at least so you have conceptually seen it and begin to recognize that a system with edges is very, very different than a system without edges. Very true also for magnetic systems and so on. In fact, there is this energy gap problem where you have Heisenberg system with boundaries, and there are energy gaps that open up because of boundaries. It's called the Haldane gap. Haldane had predicted this in 1989. Of course, Haldane much later got a Nobel Prize for some of this work, but it was an illustration of how important boundaries are in affecting the bulk properties of a system. And part of that physics is what you're seeing here, how the edges turn out to be very important. In fact, that 1989 paper cost Haldane his tenure. So Haldane was a British-born physicist who, I believe, he got his degree in Cambridge, and then he did a postdoc, and he got his first job at University of California at San Diego. And Haldane was remarkably unproductive as a professor in San Diego because he got fascinated with all these boundary value problems, and he couldn't make much headway because they were very difficult. But he was coming up for tenure in 1989, and it was in that same year that Haldane wrote this paper. And of course, nobody could really evaluate this paper. It had just been published. It hadn't penetrated into the scientific community much. And people, naturally, when you publish a result which is unusual, people are skeptical, and that's how science is. So when external reviewers wrote for Haldane, they basically said this guy is very unproductive, and they did not see that he could be tenured in their institution, comparable institutions. So Haldane was denied tenure in San Diego. So Haldane was out of a job. However, I think he got initially some kind of a temporary position in Princeton because he knew people, and not everybody was that unkind. And of course, Haldane later became a full professor at Princeton, and he did go on the basis of this work and subsequent follow-up studies to win the Nobel Prize, right? So this is not the first time this has happened, but it has happened. So edges are that important that one can lose his job in San Diego and get a tenured job and become a full professor just in a few years in Princeton. But going back, this is quite non-trivial. I'm actually not showing you any of the calculations other than pointing out that this transformation is the first quantization transformation, and then the second quantization transformation comes around. The first one works for the Fermi operators, the second one works for the Bose operators, and then he's replacing it by this part here. So difference is AI dagger AI here, and AI dagger, and AI. And this one is more restrictive. CI, CJ, C dagger I, C dagger J, or 0. So the difference is very minute, but that difference is enough to trigger. This is the same, of course, trigger the difference. And so when you actually do the calculations with this kind of a relationship between the AIs and the CIs, your Hamiltonian looks almost the same in general, but exactly the same in XY. The XY model is therefore very special. In fact, this model is basically a model for a free electron gas. A free electron gas is basically a liquid of non-interacting electrons. Electrons can hop. Electrons can, but they don't have to interact for hopping, right? Hopping is a kinetic process. So this is just a hopping term, this first term here. And then this is this thing comes around where both are created, and then the complex both are destroyed. So you have a hopping of Ci, you have a hopping of Ci plus 1, creation of Ci and Ci plus 1, destruction of Ci and Ci plus 1. That's what you have. For that, you don't need much interactions. So interactions are essentially suppressed. So conceptually, you're going from an XY model, which is a interacting spin model, to a non-interacting electron liquid. You're mapping from a spin model, XY spin model, to a non-interacting electron liquid. So let me now take this concept a little bit further. If you now take an interacting Heisenberg model, so you have SZI plus 1 in the Hamiltonian, that then would translate intuitively to an interacting electron gas model. Makes all the difference in the world. It no longer becomes solvable. When it is XY to this transformation, it's a non-interacting electron gas. When it's XYZ to this transformation, it's an interacting electron gas. And of course, interacting electron gas is a very complicated problem. It has different properties. So Heisenberg model and XY model, therefore, are very, very different in the physics that they bring up. Magnetism is probably the most fascinating field in the universe. So anyway, I'm not going to go to this problem of boundaries. That has two parts, acyclic problem, c-cyclic problem. Let me not get into that. But coming back, what Hong had done in this paper, which I showed you last time, was he took the XY model in the second quantized language and took an infinite system, imposed the scalar product that involves now the anti-commutator, which is going to be appropriate for fermions. He calculates the Fs exactly, and if he starts with F0 as some operator Cn, he can actually calculate exactly what Fi is. This is Fi. Fi is I minus I, Cn plus 1 plus Cn minus 1 divided by 2. Comes from the commutation, comes from the new revised recurrent solution, the one that we just talked about. And if you apply this, then you end up getting F1 equals I Cn plus 1 Cn minus 1, and Fi as minus I, this is over 2, and this is Cn plus j plus Cn minus j over 2. Fj equals that. So in general, all Fs can be calculated. Therefore, all length squares can be calculated, as you see here. And in a very beautiful result, he calculated all the deltas. Everything came out to half at infinite temperature. The infinite temperature is very important. And then this, of course, we know it's a Bessel function. We have seen that before. We have seen something very similar for harmonic oscillator chains. We have seen something similar for the XY problem. So he talks about that here. There's something similar also happening for the two-dimensional electron gas. And at infinite temperature anyway, you can calculate the full evolution of the dynamical variable. The first term is a Bessel function along with Cn, and the second term is a nth order Bessel function along with the F nu. And then he goes back by doing the transformation from the second quantized Hamiltonian back to the Heisenberg Hamiltonian, sorry, XY Hamiltonian. But he calculates as Cnt as Cn. Do you recognize the symmetry? Of course, he has said gamma equal to 1. But this is an XY model. He goes for the transverse spin as Z spin. Z has the same kind of relationship with the X spin as the Y spin. So as Z spin's dynamics is very special and symmetric. And this result at infinite temperature, which is this result here, as it turns out, was first calculated by this Dutch physicist Niemeyer in 1967. So this checks out as the correct result. But what Hong did was Hong said, okay, fine, I'm going to do a high temperature expansion of this result because it's a simple enough system that I can do it. Now look at what happens. While this is real, this is not real anymore. Remember I told you that autocorrelation function has no obligation to be real at finite temperature. The first time you see complex terms entering, that doesn't mean there are no other real terms, but complex terms enter. And I've written here to remind you that this is the case we studied for the XY model earlier. And that was Sx j of t Sxj, not Szj of t Szj like here. This is more symmetric. This is different. Commutations are different, defs are very, very different. And that is the reason why the result for the XX and YY correlations are so different. It turns out to be a Gaussian. So in one case, you have a Bessel function, oscillatory like that, in relaxation function. In the other case, a Gaussian. So now we know all of them, X, XX, YY, and ZZ. Now, you may say, oh, this is great. We know all of them. Nice. Who cares? Okay, there is a good answer to that. The good answer is that you are an experimentalist. You have looked at that paper I showed you by Robin Stinchcomb, where he listed over 2 tables all the materials that have XY, Ising, and all these behaviors. And you pick a system that is Heisenberg. Okay, forget Heisenberg. You pick a system that is XY. Now, when you do neutron scattering, you actually do neutron scattering on a powdered sample of the system. You take the actual material, you break it down into fine powder, very, very fine powder, and you bombard it with neutrons. Neutrons get scattered. You know that the system is described by an XY Hamiltonian, but which spin's data you are getting, you don't know. It's a dust. You're getting correlation functions which has XX, XY, which may be 0, YY, YZ, that may be 0, Z, you have everything mixed up, right? So when you actually do an experiment, your result will have all the properties typically mixed up. It is very difficult to do an experiment to just measure XX alone without turning on a strong field or something like that. So in real world, you're always going to get a soup which has XX, YY, and ZZ correlations mixed in. And if your powder is a very high quality powder, they'll be more or less isotropically mixed in. And that is exactly the reason why you need to not only know the Gaussian result we had, but also the ZZ result, which gives you the Bessel function. So therefore, this is the main thing that you get out of this kind of a study. You are now able to actually study the scattering from powders by doing Fourier transforms of these results. And these results are very distinct, actually. So in every case, although practically it is very difficult to calculate, but in every case, when powdered samples are involved, which is normal, you have to average over XX, YY, and ZZ correlations. Now we are ready for moving beyond this to stochastic processes. So we can just start a little bit. Stochastic process. As I told you earlier, stochastic process means that there is no memory of earlier incidents in a system. How you apply stochastic process studies depends upon the system. I gave an example of the stock market, for example. And I then also argued that stock market also has its memory. We can't really say stock market is stochastic, but yes, we can approximate the stock market as stochastic if we are not doing day by day, but doing maybe once a week, or maybe, once every 5 days or 4 days. By that time, it has no memory of what was happening before. It becomes pretty darn stochastic. But if you take a deck of cards and you start pulling out cards at random, that is pretty stochastic. The deck of cards doesn't remember what cards you took out in the previous pull. So you can visualize processes that are basically pretty stochastic. So stochastic processes are also known as Markov processes. By the way, did I send you guys the review article by Chandrasekhar? No. Okay.
Sound familiar now?
Okay. So the reason why I guess I didn't is because I didn't want to overwhelm you with because I want you to focus now on actually doing a study of the memory function for those spin systems and calculate them, plot them out. I want you to focus on that. But in this context, it's very important to be aware of the fact that the study of stochastic processes, or Markov processes as they're called, in physics and astronomy was pioneered by S. Chandrasekhar, who won the Nobel Prize for predicting the existence of black holes. So Chandrasekhar got his PhD in 1933 from Cambridge, and subsequently he became a professor at University of Chicago. And Chandrasekhar was a very interesting guy. He used to work alone. He didn't care to have any real collaborators. Chandrasekhar did not take many students. He took very few students. And he was not known as an easy advisor to work for. And in part, that was because he desired that all his students would have the exact same work ethic as he had. By the time I first visited University of Chicago in 1995, Chandrasekhar was, he died, I think, in the same year. He died shortly after my visit, but he still used to come. He used to come at like 6:37 in the morning, and he was there all day. He always used to be well dressed, nicely suited. He was an extremely, kind gentleman. He was very gracious, and his standards were incredibly high. So there was a time when Chandrasekhar used to spend his time in the Yerkes Observatory in Wisconsin, although he was a theoretician. And Yerkes was University of Chicago's observatory. It still is, actually. It's in Wisconsin. So Chandra used to commute between Chicago and Wisconsin twice a week. And he used to commute because, like in this class, he had only 2 students. And the students were Xian Yang and T.D. Lee, both of whom got the Nobel Prize in their early 30s, in 1950s, right?
Phase transition, guys.
Yes, phase transition guys, but they got the Nobel Prize for their work on parity violation. That was actually what they got the Nobel Prize for. So the department at the time was very queasy about asking Chandrasekhar to teach this class because he was not living in Chicago. He was living in Wisconsin for University of Chicago job only. But Chandra said, no problem. These 2 students are very good, and I'm more than happy to come and take my class at University of Chicago. Anyway, so Chandrasekhar in 1943 This was well after he did the work on black holes, by the way. He wrote a paper, and this paper was in the Reviews of Modern Physics. It's a review journal. This paper splits the write-up of the paper into a great many chapters as opposed to sections. It's like a book. And Chandrasekhar's paper in Reviews of Modern Physics had 89 pages. It's a big review. And the title of it was Stochastic Processes in Physics and Astronomy. So it starts from scratch as to how to use the idea of memory-free dynamics on a lattice and how useful it becomes across all sciences, and set the stage for the study of physics of stochastic systems essentially for the first time. So Markov's original work was in 1916, but Markov's work at the time was neither popular nor recognized. So Markovian dynamics, stochastic processes as you study today, forgets to mention that this was also one of the seminal contributions of Chandrasekhar. That's why it's important that you actually have this paper and look at it. I'll send it to you guys. Very easily available. So the idea of stochastic processes as it is taught today is different from the way Chandrasekhar did it. But both are important. Because I didn't study it like this, I learned it from Chandrasekhar's work. And then there was a time when I had to actually do a calculation of air flow through filters, how a filter jams up. Because air has impurities going through a filter, and some of the dusty stuff will get stuck in the filters, which means the filter will slowly age. And as the filter ages, it gets jammed up until you reach a stage where the filter is nearly completely jammed up and airflow will stop. It is trivial to see that older a filter, in principle, it can be a better filter because the pore sizes will shrink, which means it will allow less and less dust particles to get through. So there is an optimal older filter that is a good filter. If you change your air filter all the time, you are allowing for more dust to go through. You're arresting less. The problem is as filters age, the dust keeps jamming up. And when the next dust particle comes and hits the filter, it also blows some old dust off. It becomes a very messy, turbulent flow. That's another problem. But I had to study this problem. I had to study this problem because the space shuttle was having an air filtration problem at zero gravity. So NASA wanted this problem solved. And I was one of the theoreticians of a group that NASA had come to. So I got a lot of funding for it at that time. And I had to literally learn to do this problem overnight. So I made each dust particle a random walker, hence a Markov system, because it has no memory of previous step, going through a filter. And just by reading Chandrasekhar's first few chapters, I was perfectly capable of deriving a scaling law of how the filter would jam up. And then we later confirmed it numerically. So it is that powerful. I mean, I could just do it overnight, pretty much, a couple of nights. I could derive it. But anyway, here you won't get so lucky because I'm going to take you to the conventional treatment. And then I'm going to give you Chandrasekhar's paper to read. Okay. So there are all kinds of probabilities. Suppose a probability of some random process happening at time t. The random process is C. So the set of values that the random process entails is C. So this is one kind of one particle probability, 1 point probability, because it only depends upon that time and that sample value. That's all. But then you can have P2, where C2 and T2 depends upon C1 and T1. P3, this 3 here is tied to these 3 sets. C3, T3, C2, T2, C1, T1. Implicitly, T1 comes first, T2 comes next, T3 comes after that. The event C1, T1 is followed by the event C2, T2. And once C1, T1 and C2, T2 has transpired at T1 and T2, these are the two events, two values that have emerged of some variable, then T3 will involve C3. So this is, in this case, T1 is earlier than T2, T2 is earlier than T3, yes, but all these three things are happening. All these three things are being measured together. So there is a concept of being measured together and measured sequentially that comes into this game. In general, the most general sort of scenario is when things are measured together. The most restricted scenario is when things are measured with some imposed condition. So there is something called 1 time, 2 time, 3 time, or n time joint probability distribution function. And there is something called n time or n minus 1 time, let's say, conditional probability distribution function. The previous things have happened, and given those things that are now frozen in stone because they have happened, the new thing is happening. So you have to learn the difference between a joint probability. Joint probability, although it requires that there is a precedence, but there is no frozen condition on this precedence. But conditional probability has a frozen condition on this precedence. So anyway, so this is the n time joint probability, and the product of infinitesimals TC1. So there's this little range here. And so this is a probability distribution function. So anyway, this is not an important slide. I want to go to this slide. How do you measure it? The way you measure it is that the n time the joint probability function, which is this one that you had here. See, everything has a semicolon. See that? So if you go back to the previous page, everything has a semicolon. See that? So if everything has a semicolon in between, it is a joint probability distribution. This, on the other hand, is a vertical bar between the nth case and all the previous cases. This means all the previous cases have happened and generated these values. Now this value is going to come because of that. So this conditional probability distribution function, by definition, this joint one is a conditional one and Pn minus 1 joint one. This is by definition. So the nth case, which here was unconditional, has now been made conditional. And the n minus 1th case is unconditional. So this is a level of simplification of this, which opens the door to subsequent simplifications. I can give you a simple example. Maybe that will help you. So I think it's in the next slide. So let me just take you there. So what is a joint probability? A joint probability is something like this. Probability that a card is 4 and red. So there are two reds. There are two red 4s in a deck of 52. 52 cards is a complete deck. There are two red 4s. There's 1 4 of the hearts and 1 4 of the diamonds. So if you're going to pull out 2 out of 52 correctly, then your probability of getting it right is 2 over 52, which means 1 over 26. This is your joint probability. Because all of these things are available to you. That's the concept. All these are available to you. And you're pulling out these two. You're pulling out these two somehow from the entire range of possibilities. Of course, a very simple system. You just have these possibilities. It's like T1, T2, T3 is not really quite there. It's just you're just pulling it out with the whole field wide open. That's it. Conditional probability is you draw a red card and then the probability of getting a 4. So if you take 26 red cards and there are 2 4s in them, red cards can be red diamonds or red hearts. And then you have the black diamonds and the black hearts. You have red and black. You don't have any other color, right? So there are 26 of the reds and 26 of the blacks. So if you want 2 reds, then those 2 reds can come out of the 26 reds. There's only going to be 2 out of those 26, so it's 1 over 13. So you're drawing a red card. What's the probability that it's a 4? Out of the 26 red cards, there are 2 4s. So you got that. So this is now different, 1 over 13. The point is, if n becomes very large, which is the limit in which everything is done, then the probability, whether it's a joint probability or a conditional probability, they become almost the same. This is not n large, this is n equal to 52 and 26, so therefore it's quite different. So again, joint probability that a card is 4 and red. And here, what is the, you're already taken out a red card. What's the probability? That's a 4. It can be a 4 diamond, or it can be a 4 heart. Here, there can be 4 hearts and 4 diamonds. Naturally, the possibilities are higher. I mean, combinations are higher, probability is lower. So this is basically an illustration of the difference between what is a conditional probability and what's a unconditional joint probability. Joint probability is relatively less often used. People generally do step-by-step calculations. And because we generally do less step-by-step calculations, we want to deal with conditional probability. We don't want to deal with joint probability. Because joint probability can be a very small number, it may not give us a great deal of insider control. But if you do a process with conditional probabilities, then conditional probabilities will have more sort of sequentiality built into it. That's the main point I'm trying to make. So I'll stop here, but I just want to point out that you can so go a step further and replace an probability of n processes, conditional probability, all right, but all of these n minus 1 processes have happened, and then this process is happening in a great simplification by a 2-time probability, where you are saying that Jn Tn is only dependent upon Jn minus 1 Tn minus 1. In fact, this is the Markov assumption. They are throwing away everything else because there is no memory. You are assuming there is no memory and you are replacing it with just the past event, immediate past event. And because this immediate past event is a great simplification, you can start from the initial state of the system, which is embedded in this P1, and then sequentially come to P2, to P3, to P4. So if you want to relate it to this guy, you can write it like this sequence. And this doesn't have any equilibrium assumption because the very first state also has a dependence on time. You can say a T1. So it doesn't have an equilibrium assumption built into it. It's an intrinsically non-equilibrium Markov process. So this, therefore, is a unconditional probability. It is being replaced here in Markov assumption by a product of conditional probabilities and the initial state's probability. Initial state changes, this will also change. Initial state changes, each of these will change. But if initial state is defined, then you can slowly sequentially build it up and calculate approximately this quantity in the Markov assumption, meaning that the last instant mainly matters. And here you are basically replacing the initial state by a time-independent equilibrium state, if you will. And therefore, it's only the difference in time that matters. And that's what a further simplification would take you to. So t minus t prime here and zeroth state equilibrium here. And t minus t prime can be now defined by your new time. So you're replacing it with that time interval only. So in this case, the importance of the initial state is lost. The importance of non-equilibrium is lost. You're starting with what would be construed as an equilibrium state, and you're coming from here to the tth point in time and the kth Markov. This is the kth value of the Markov process. So, sorry. So this equation and this equation allows you to write pk of t as a product from one state to the next, L equal to 1 to n in this approximation of pk of t minus t prime from L, and then the probability of getting to t prime from the jth state to the state. So essentially, it is this equation. This equation written in a slightly more simplified form without even introducing the assumption of equilibrium really in its non-equilibrium form. And this equation is often called this Chapman-Kolmogorov equation. And this summation many times is replaced by an integral. So Chapman-Kolmogorov equation becomes an integral equation in continuum language. It's also called this chain equation, meaning all these chains of events are happening. So these are the preliminary ideas of what emerged back in the early 1900s when Markov did this work. You may have heard the name of Chapman. I don't know if you have. Chapman is very famous for his book on hydrodynamics. There's a book called something, I have it here. It's by Chapman and Cowling, T.G. Cowling and Sidney Chapman. Sidney Chapman was a very, very famous mathematician, actually. And so it's not a surprise that Sidney Chapman and, of course, independently, Kolmogorov, they used Markov's ideas to simplify the whole concept of zero memory dynamics to some form of a manageable equation, which is this Chapman-Kolmogorov equation. Let me stop here now. We have had a long period already. So what I want to actually take you to is this Chapman-Kolmogorov equation itself lends itself to something called the master equation. And this master equation is widely used in statistical mechanics. The idea of stochastic processes is embedded in here. And it is written in terms of transition matrices, much like in quantum mechanics. So this is like a transition matrix where you're going from L to K. And this is just the reverse. What if you revert back from this is the starting state K to L. If you revert back, there is no change. If your probability of reversing back is very little, then there is some change. That's how it works. So this is a gain probability per time. It's a loss probability per time. And so the master equation is essentially how the probability is changing as a function of time, depending on the gain probability and the loss probability. And if the system is in equilibrium, you can imagine that the gain and the loss probabilities are the same. And that leads to the beautiful concept of detailed balance, which is another way of saying that the system is in equilibrium and gives you some beautiful properties and calculable things. So this is a very tricky matrix, actually. Nothing like probably you have ever seen before. And so I'm going to spend some time developing the physics of this system on Thursday, and hopefully trying to give you a better feel for it before we get to nonlinear equations as our next target area, because that's a more vast area. I want to spend time on it. But here, it's also a very fascinating kind of area of work that a lot of people have made great use of in doing deeply non-equilibrium studies, as well as extremely powerful equilibrium studies of optics processes, of in molecular physics, of transition processes. It's used in biology a great deal. So master equation is a very sort of useful equation to have. But the whole idea of what we are doing here basically goes back to where I started, that you have this joint probability idea. The idea of a joint probability being that somehow over time sequence, the probability of something happening is a unique probability. Probability the system reaches this n-1 state is a unique probability because it doesn't really jump to this state. It comes to this state over a sequence. And this sequence has its own memory and physics and everything going along with it. And it's obviously very, very difficult to track the history of a system to understand the system. And so what you do is you reduce the problem under the Markov approximation to what happened to the system in the immediate past instant, and use that as your basis for constructing the description of this complicated thing that you have. And to write this equation, of course, you envision this equation as what happened in the immediate past, and then what happened before that, and before that, and before that. So this is the first process of the breakdown. And the second process of the breakdown is you essentially break it down to a sequence of these two-time probabilities. And this is already under the Markov. That's the main point. And then you can start from first state as an unstable time-dependent state or a stable equilibrium state. And when you do that simplification, stable equilibrium state simplification, that opens up you see, this is an equilibrium state. There is no JT, it's only J. And so that opens up the door to write down the master equation that I just said. So the master equation is essentially coming out of the Chapman-Kolmogorov equation. So anyway, I'll go through this again on Thursday and take you through. I mean, this is not an area of research in which I have really done much work, excepting for the little calculation I mentioned about the dust problem. But for those who do this kind of work, a lot of techniques have developed. And this is one reason why I want you guys to study a little bit Chandrasekhar's work, because Chandrasekhar approached this problem from more of a practitioner's point of view than a theoretician's point of view. I'm doing a theoretician's point of view, but Chandra approached it as a practitioner's point of view. And when I learned it, I didn't learn it this way because I never had it in my StatMech classes. So I only learned the practitioner's approach from Chandrasekhar's paper. And I think both are important. And Chandra's paper is very followable. He wrote very well, very terse, but he wrote very well. He was not repetitive. So I think you will find it useful. So I'm going to send it to you today. So tomorrow, if you can find some time, take a look at it. You'll get another dimension to this understanding that is non-textbook, more for somebody who is trying to learn to use it. I assure you that if you are planning to be a physicist, the study of this master equation is not going to let you down, because sooner or later in life you're going to run into some kind of a master equation that you cannot avoid. It may not be exactly this, but it will be a cousin of this. That's how, I mean, imagine if you are describing optics processes, quantum transition processes in a charged gas. Electrons are bouncing up and down between higher energy levels and lower energy levels. Your master equation is basically the equation you learn in quantum mechanics, where you have these transition rates. So the concept is universal and very powerful. I'll also talk about this theorem called Gershgorin's theorem, which tells you how to deal with this W matrix and its properties. It's a fascinating matrix to learn to deal with. I wish I had enormous expertise in this also, like I have in the other ones that we have just studied, but I don't have that expertise, I'm afraid. I only know what a typical student knows. This one, I don't have great vision and expertise. I have rather limited exposure to it. But that's how it is. I mean, we don't know everything well. We only know we are specialists in certain things, and that's where we can really share that insight. And I'm just delighted that in a small class like this, because we are able to do it online, I'm at least able to share with you some of the expertise that I would never be able to share with you in classroom, because it just is so detailed and so involved that, and I can't go back 2 boards in the flip of a finger to show you what I just showed you to connect. It's just not there. So I've never been able to do it. So that's the exciting part. I wish I had the same level of expertise in all these areas, but nobody has. So it's what to do. All right. Thank you for bearing with me. We had a long class. Tuesday we will, not Tuesday, Thursday we will stop recording.